This talk is going to be a bit different, as we're going to be looking at exporting metrics from the application side. Last year, my company decided to revamp the Prometheus Ruby client to bring it up to the standards of the other clients. It was quite an unusual project, and I hope you'll find it interesting. First of all though, hi, my name is Daniel, and I work for GoCardless. We are a payments company based in London. As you probably noticed now, though, I'm not originally from London, I come from Argentina, so in case you're wondering, that's the accent. Now, for us at GoCardless, uptime is very critical. And that means, among other things, that having good metrics for our apps is critical. And as you probably guessed by the conference name, we mainly use Prometheus for this. Now, we love Prometheus, but we had a bit of a hard time getting it to work with our main application, which is written in Ruby. Now, to see why, let's look at how metrics are exported. As you know, Prometheus periodically scrapes a server for their numbers. So we have our apps, which in our case are mainly written in Ruby, and they're keeping a bunch of counters in there. Prometheus hits us every few seconds, and you return something that looks a bit like this, and for most languages you just use the appropriate client library and the story ends there. The problem we had is that in Ruby land, and by the way also in Python land, this is a bit trickier because Ruby and Python have a global interpreter lock, which doesn't let you run your code in multiple threads at the same time. Because of this, our web servers are not usually multi-threaded in Ruby. This doesn't parallelize well. Instead, we tend to use separate processes. Processes don't share memory, which solves the same problem that Gil is trying to solve, and everybody can run in parallel, ignoring each other happily. This is, for example, how Unicorn works, which is one of the most common web servers in Ruby. When Unicorn starts, it loads your app, and then it forks itself into a master orchestrator process that's listening to requests, and a bunch of worker processes that are actually going to be working on them. When a request comes in, the master sends the request to a worker that is free, and then takes the response and sends it back to the client. This system works great. It scales really well across cores and is the way that most Ruby web apps are running in production. However, for the Prometheus use case, this is a bit of a problem because now that we have multiple processes and they don't share memory, each process will have its own internal counters. When Prometheus polls and asks for your metrics, the master process will send a request to some random worker, and that worker will report its numbers. But this is never what you want because this number is only a partial view. What you want is the global view of all of these processes added together. But because these are separate processes, there's no way for any single worker to see the counters in the other workers to be able to add them. This is by design, and it's the main reason we use separate processes, but for the Prometheus use case, this is a problem. And so, since most Ruby web applications are running in pre-fork servers, and since the Prometheus Ruby client didn't have a solution for that multi-process aggregation, that meant that lots of Ruby projects that wanted to use Prometheus basically couldn't. And we definitely had this problem. We were using Prometheus, we wanted to have metrics for our main application, and we couldn't. And it wasn't just us. This had been the case for quite some people for quite a long time. Also, the Ruby was one of the first libraries to be made, and it was very early in the lifetime of the Prometheus project. This was before the community had figured out what some of the best practices were, for example, so it also had a bunch of other issues, like the way it validates labels. There were some workarounds out there. GitLab, for example, forked the official client and had a multi-process solution that's based on memory maps. But it wasn't getting merged into the official repo, and it also shared all of the other issues with best practices, so we preferred not to use it. Discourse has a different solution, with a separate process running alongside your app, which your worker process would push metrics to, and then that process would report the totals to Prometheus. This one also didn't mesh very well with the way we wanted our setup. But mainly, we didn't want to be on a fork. We much preferred to use the official client, so we got in touch with the maintainers, we roughly agreed on a plan of action, and we decided we'd do pretty much a rewrite fixing all of these things. But there was one more thing to consider. The Prometheus maintainers really care about performance for these libraries, and for good reason. Instrumentation should be free for your app. If you want to increment a counter inside a tied loop, for example, you should be able to do that and not notice it. And buried in that long discussion from the 2015 ticket, there was a target. One of the maintainers said basically that incrementing a counter should take less than a microsecond, which prompted an interesting discussion of whether this could even be done in Ruby, with comments including, surely Ruby can't be that slow. And my favorite ever, I guess there's a reason people like writing C extensions? So whatever we did to solve this had to be fast, and we had an actual target. Finally, there was one more thing that we and the maintainers agreed that we wanted to do. Instead of having our metric classes with their numbers in an instance variable, like this, we wanted to change this so that these numbers would instead be stored somewhere separate. We wanted to have stores that were interchangeable and keep all of the numbers there. So we go from something like this to something more like that. The reason for this is that different projects would have different needs. Some people would be working on a single thread, a single process, and some may really care about performance, whereas other people have a web app in multiple processes hitting a database over the network, so who cares about microseconds at that point, right? So this was the plan we had. We were going to support pre-fork servers, we're going to abstract away the storage of numbers, We wanted to follow all of the current best practices, and whatever we did had to be fast. Now the first question is, can we even do this within that time budget? Now, according to this exchange, this either could or couldn't be done in a microsecond. And the truth is, at the time, I had no idea. I am mostly a Ruby backend developer, which means my normal intuition for code timings are milliseconds length. So the answer to this is a bit long, but the short version is we basically can't. Let's look at this. Like, if you just go ahead and do this, you just increment the hash. You can do this about 12 times in a microsecond, which is great. It's well within our budget. But in our case, it's not that simple. Because if you think about it, why are we even using hashes instead of just having an integer? And the reason for that is labels. In the Ruby client, labels are specified with a hash of keys and values, because that's the interface that makes the most sense in Ruby. And we store our numbers in a hash where the key itself is also a hash with those key value pairs. Now the problem is, when you're using hashes as the key for your hash, whenever you need to find an entry, you're going to be comparing hashes to hashes instead of comparing constants. And this is much, much slower. Now, how slow depends on how big those hashes are. In our case, how many labels you have. So for example, if you have 3 labels for your metric, that's going to be 60 times slower, which is pretty terrible. Now, according to best practices, most metrics should have no labels. So if we take that as a benchmark, then it's better, but it's still 9 times slower than with a constant. And you will notice that that's already quite close to the budget of 1 microsecond, and we're only incrementing a hash here. In real life, we need to add some validation and processing to these labels, and we're not even thread safe. You put a mutex around this, and now you're at about 1.5 microseconds per increase, and we blew our target. So it turns out, in our particular situation, we can't do this in a microsecond. And now we're already past our target, and we're still in a single process. I mean, we can optimize this a little bit, but any multi-process solution will definitely not be in budget. But what's important to me is that we should keep to the spirit of this target. The important thing here is we really care about making this instrumentation as fast as possible. And because this will impact lots of projects for lots of people, it's really worth investing a lot of time into that. So this is where we were. At this point, we have an idea of times, and we can exchange stores very easily. Now we need to actually share the numbers across processes. And the way we approached that was to basically experiment a lot. At this point, we pretty much started trying everything that we could think of, because with these separate stores, it was very cheap for us to try different things. And I would like to walk you through 4 of these experiments that we did. First off, let's make this really easy for ourselves. Ruby has this unusual data structure called a p-store. Basically, it's a hash backed by a file on disk. Every time you set a value, the entire hash gets serialized to disk. Every time you read a value, it's all read from disk again. And the file has a lock around it, so you can actually read and write the same file from multiple processes all at the same time. Everybody sees the latest information, and it will be safe. And if you think about it, this is pretty much exactly what we need, right? We have this global hash shared by everyone. All the processes see all the data. We're done. Performance-wise, though, this is pretty terrible. Now, if you think about what we're trying to do here, we're basically trying to have a chunk of memory that is shared between different processes. As a complete aside, one of the great things about GoCardless is the amazing people I get to work with. Now granted, some of those people are trolls, but the trolls sometimes have good ideas. I mean, SQLite was probably not going to be the right solution, but like, he got me thinking. You know what's a great way of having a chunk of memory shared between processes? It's my good old friend Redis. Redis is basically that, right? It's a chunk of memory running in a process alongside your app. All of your processes can access it, and we all know it's super fast. So this sounded like exactly what we need. And actually, the Prometheus client for PHP uses Redis for this exact reason, so that was pretty promising. So I wrote up a little store that would use Redis as a backend. I knew this was going to be the solution, fired on my benchmarks, and it's actually much slower than just dumping the entire hash to disk every time. And that makes sense, right? I mean, talking to Redis involves a lot of ceremony and networking, even if it's in localhost. Compared to just writing a tiny file within your own process, it really had no chance. And to be honest, this was surprising and disappointing, but it was also a relief. I didn't want to force everyone to have a localhost Redis in each server just to have Prometheus metrics, so it was kind of good that this didn't work. At this point, I had no choice but to face a giant elephant in the room. The consensus from pretty much everyone on how to solve the multi-process issue was that we should use memory maps for this. This is, for example, what the Python client does, and also the GitLab fork. But during most of this project, I was trying to avoid them. I really wanted to find another way. And the reason was mostly that I didn't really know how to use them, and I had heard someone had, at some point, some problems with Secfaulting, which is a bit scary. Now, as a super quick introduction to what we're doing, we were going to be using a shared memory map file. What you do is you map a file to memory with the shell flag, and then if two processes do the same thing with the same file, they end up reading the same page in memory. So one can write to this memory and the other one can immediately see this data. This is actually famously one of the fastest ways to do inter-process communication, so I can see why everyone was suggesting to use this thing. It does sound like the perfect solution. There's only one tiny problem. mmap is a syscall. Do you all know how to call a syscall in Ruby? You don't, you do it in C, or something like C. Now, granted, there's this thing which has the most hilarious line I've ever seen in official documentation, but it's not particularly useful for this. And even if you actually manage to call mmap with this, now I have a chunk of raw memory and a pointer to it. Now what am I going to do with that from Ruby? So we need some sort of gem to use this, preferably something written in C or Rust or something like that. Unfortunately, there's this, which is maintained by one of the core Ruby contributors. This is Aaron Patterson. He goes by Tenderlobe on the internet, and he's normally hacking on the memory management part of Ruby, so this actually filled me with confidence. Now, how do you mmap with this gem? Well, you basically make a file, you initialize it to a certain size, say 1 megabyte, and then you init an mmap. And now you have this m variable, which behaves sort of kind of like a byte array. Now, importantly, it is not a Ruby array. The mmap gem is doing a bunch of magic to make it behave like one. But if you have a bunch of bytes to write, you then basically set a range on this thing, and that'll do it. Now, the tricky bit is turning the stuff you want to store into a bunch of bytes. Now, I shamelessly stole this idea from a branch that Julius Volz wrote. Now, the short version is you store the labels encoded as a string, and then a float with the number that you want, but you keep track of where in the file you put that float, in a hash that you keep in memory, this add positions here. Now, the next time you need to update that float, you just need to find that position and change those 8 bytes. You don't have to change the entire file, just those little 8 bytes. Which is pretty clever, right? I wouldn't have come up with this myself, so thank you, Julius. Now, you may be thinking, rightly, how fast is this? And the truth is, it's pretty fast, actually. It's pretty decent compared to all of our other options so far. But there's only one problem. In addition to having a little benchmark script that I was using to time these things, I had another script that would stress test these stores. Basically, it would do terrible things to them just to make sure they were safe. It would have a ridiculously high number of metric with lots of different labels, and it would use it from different threads, from many different processes, all competing for the same file. Just hammering it to make sure it's solid. And as soon as I ran this script for the mmap store, I got one of these. Now, I don't know about you, but until this point, I'd never encountered a Secfault in Ruby, at least not one that was my fault. So now, I'm using this gem that does some memory voodoo that, quite frankly, I don't fully understand, and now I got a Secfault. And this was kind of the reason I was trying to avoid mmaps, right? Like, I was worried this precise thing might happen, and now it did. And given that this gem was written by Tenderlobe, and it was being used by me, it was most likely not a bug in the gem. I'm almost certainly using it wrong. But it's a very obscure gem. Not many people need to do this. So there's not much documentation. I haven't found anyone actually using it. It's kind of hard to figure out what I'm doing wrong. I'm also not very strong at C. I still tried to look at the source code, but it's a giant file with 2,500 lines of code. I didn't really manage to figure out what the problem might be. Through experimenting, I did narrow it down to the code that resized our mmap if the initial size wasn't enough, so that 1 megabyte, sometimes it needs to grow. I still had no idea why it happened, but at least I could reproduce it reliably, and so we did what we all do when this happens. We try random stuff until something sticks, right? Took a while, because I had no idea what I was trying to do. But I did end up making the Secfault stop through an elaborate dance of like closing the file, reopening the file, resizing the file, closing it again, reopening it again, remapping, and for some reason the Secfaults didn't happen anymore. Now, if you have a problem, you don't understand the problem. You try random stuff until the problem stops happening, but you don't know why it was happening or why it stopped. How confident are you that that's not going to happen again in production in some random server, in some random company's mission critical app? I really wasn't. I did not like this one bit. And this is precisely why I was avoiding the memory maps at the beginning. So this was fast, but I wanted to keep looking. And this takes us to our final solution. Now, if we look at this code again, we're basically working with a thing that looks a lot like a file, doing the kind of things you would do with a file, which just happened to be doing in memory, which was faster than normal files. But what happens if we ditch the mmaps and just do this to a file? Pretty much the only difference is, instead of setting a range in something that's pretending to be an array, we need to call these functions to jump around and to write, so basically file seek and file write. Now when changing a value, it now looks like this. And while it's a file, it's super efficient because you're just doing one seek and writing 8 bytes. You're not dumping the entire hash like with the pstore. And we are also using separate files for each metric. So if you're multi-threaded, you're going to have less contention on those files. And now you have no memory maps, no C, no Secfaults, nothing fancy, just plain old boring Ruby writing to files. Now, obviously, the problem with files on disk is that they're kind of slow, right? And so if you're thinking, how slow is this? This is kind of insane. This completely blew my mind initially. Like, considering how slow I expected this to be, I couldn't believe this. Now, it makes sense because we're basically not f-syncing. So we're not actually touching the disk. We're really just doing this in memory. And it's fine because we don't really care about this data staying if our process dies. But it's still surprisingly fast. And if we compare this to memory maps, we have no external dependencies, no risky C code, definitely no Secfaults. It's compatible with all versions of Ruby, which we care about because we want to support JRuby. It is 100% understandable by any Ruby programmer. And very importantly, there's nothing in that code that keeps me up at night. All of this for just 3 extra microseconds? This was a complete no-brainer. And we were done. We ended up going with this as our final solution because it was fast enough. And we think that the trade-off is more than worth it for the peace of mind that this solution brings us. Now, we did make a separate gem with the memory map store, and it has a better solution for the resize. I think that's the correct way, and I think it's stable. But we don't trust it. If you really want those 3 microseconds back, you can use it at your own risk, but we don't really recommend it. We don't trust that thing. So this is where we are now. After the rewrite, we ended up with 3 built-in stores for different scenarios. So you can have if you have a single thread in a single process, or multiple threads in the single process, or multiple processes. You now can configure how to aggregate values, because now that you have multiple processes, you can have multiple values. So customers and histograms, you just want to sum them. But for gauges, that doesn't really necessarily make sense. It depends on your use case. So gauges will default to all of the time series where they get tagged with a process ID label. But you can, for example, take the maximum or the minimum or the most recent one. We now require declaring all of your labels up front when you register the metric, which is what the best practices indicate. We are much better aligned with Ruby conventions. For example, we use keyword arguments, which is where the Ruby world is going towards. We ended up doing a lot of profiling and a lot of performance work as part of optimizing the stores, and we ended up optimizing a lot of little things here and there, especially histograms. Histograms are a lot faster now. And finally, we now have a benchmark script. So if you want to try different scenarios and see how this affects your particular performance in your app, you can now measure it fairly easily. So we had that running for several months in production at GoCardless, and then our PR got merged and we released 1.0. So since late last year, everybody can now use Prometheus with Ruby. So if you're a Ruby shop and you had this problem, now you can have your metrics. And as part of this, we ended up becoming maintainers of the gem ourselves, which was pretty nice, and it allows us to do more work on it. Which is important because there are still some issues, and we still really need to put some work into this. First of all, we have the too many files problem. Now, to keep contention low, as I mentioned, we keep separate files for each metric in each process. That means if you have a lot of metrics, you're going to have a huge number of files, and you end up getting problems from that. So what we want to do is give you the choice to trade off having maybe more contention but fewer files, and maybe that'll help. Most importantly, we focused all of our attention on having the flexible stores and having good performance when incrementing counters, but we had a pretty large blind spot. The way we structure things, exports can get really, really slow if you have lots of metrics, around tens of thousands of metrics. So we're now starting to work more seriously on this because more people are being affected by it. We hope to have a response reasonably soon. Finally, we want to support open metrics as soon as it is ready. So we have already started working in this direction. And that's all I have for you today. I hope you found some bits of that interesting. Thank you very much for listening.
So first question, how do I connect 2 clusters?
I don't think that was for me.
Yeah, that's an old one.
I mean, I hope it's not for me because I couldn't even start.
No, sorry, that's an old one. And that's the only one in the Zoom Q&A.
Excellent. So it was super clear.
There is interest in your streaming setup and in your video pipeline. I assume it's OBS and a green screen.
It's not OBS. It could have been. If I were streaming, I would have used that. The green screen you can see right there. The setup is insane. I'll retweet it, hashtagging you guys so you can see it. It's a bit mad, but it kind of works. I'm using Camtasia, just for reasons, but you could have used Premiere or whatever. OBS is not as fun to edit the video afterwards.
Okay. I don't see any other questions in any of the channels, so.
Well, you're gonna have to wing it now.
Yeah, I mean, you can.
I can ask some questions.
Oh no, not again. Hi, Ben.
So I'm Ben. I am also part of the maintaining of the Ruby, although I don't do a whole lot. I just kind of give Prometheus advice to the GoCardless team. They've done a great job of maintaining this. The mmap thing, yes, is very, very, very fragile. It took us quite a long time to get the GitLab fork of the. So GitLab took the same code and we forked the same Julius Volt's mmap branch and began our development of a file-based backing store using mmap. And what we ended up doing was we dropped the mmap gem and just brought over the C code and then basically made the C code self-contained within our gem. So we no longer use the upstream mmap gem because there were some bugs. And so we basically started implementing more and more of the metrics handling in C, and then just used it more as a real library. And that solved a bunch of the crashing and segfaulting and other race condition bugs. In addition to the really, really hard part, which I believe you ran into with the mmap and the file-based storage, which is reading back metrics from the file storage was super slow, especially when you get to say 20, 30,000 metrics on a unicorn. And I don't know if you've had any additional thoughts on how to make that part faster.
So I've had thoughts. I actually think of you very frequently because I want to get you guys on the official client rather than on your own fork. And I know you're the ones that have the biggest problem with this. So part of the problem I have is we have to sort of balance code cleanliness and just elegance, if you will, with performance, because the abstractions that we have don't really help. Like, it's not just reading back the files is slow. You can read the raw files, it's not that terrible, but what you end up with is now you have to massage all of these hashes to turn them into 1 mega hash. And also you have things like you don't want the exporter to be talking to the stores directly because that's kind of dirty. But if you don't do that, it's going to be slow forever. So we're trying to sort of strike the right balance there to make it not disgusting, but also fast enough. I have a bunch of thoughts, but I don't have any exciting results to report yet, but I would love to. So Stefano Torres is asking, what about clusters of distributed apps? A centralized store like Redis is the only way there. So what you would do there is you would basically report. So you have a bunch of boxes and each box will report its metrics and then you aggregate when you're querying, or at least that's how I understand it as a best practice. You don't want to have different machines centralized into one Redis store and then reporting everything from there, because that would basically obscure if you have problems in one machine or another. Correct me if I'm wrong, Ben or Richie.
Sure, yeah, no, that's absolutely correct. You don't want to use a central store for an entire fleet of applications because some of those may be taking more or less traffic, or say one server is having out of memory problems or out of disk problems. You want to make sure that you know that particular server is broken versus all the other healthy ones. I got a question from the Q&A. Of the list of features on the roadmap, which ones are you prioritizing?
Yeah, hi Josh. So the one I would like to prioritize the most is this export speed. We've had other issues come up, so other GitHub issues come up with people reporting that. So I would really like to get that as soon as possible.
Another question from the Q&A. When do we need to read from files when instrumenting?
So I'm not sure I understand this one correctly. If you're instrumenting your own app, you wouldn't need to do that. Like the client library would do that for you. It basically transparently handles those files. So you would ideally not even notice that those files are there. At most, if you have a persistent file system, you'd have to, these files are stored in a /temp directory and you want to empty that. So if you're in containers, that will come for free. But if you're basically rebooting your server, your app server on the same machine, and you keep files from the previous runs, you want to kill those files. Otherwise, you're going to be reporting sort of the metrics of the previous run instead of starting again from zero.
If there's no more questions, I just add a comment from the Python side, which has a similar implementation. Now, we've had a few PRs over time. The community has been kind enough to basically tune our buffers and so on. So the reading itself is not a problem. The problem is process churn, because we create 4 files per PID. And that's fine if you have 16 workers, but not when they change every 30 seconds. And that's what the big problem is there. Yeah, yes, we have lots of users doing Dash, and that's where the problem is. And to be clear, our keys inside the files are just encoded JSON, but we don't have to read it too often, so that's fine. So there's been talks about compaction, but unfortunately everything proposed was not thread safe because, well, another process can start with the same PID, and we need to make sure that's correct. And we have no control over this because we don't know if people are using Unicorn or multi-process Python stuff or anything. So if you ever find a solution for that, please let us know.
Yeah, so I'll take your 4 files per process and raise you a file per metric per process, which I now regret. It did make it faster to write, but I thoroughly regret that. That's the other thing I really want to prioritize, giving implementers the option, whether they want that if they're seeing a lot of contention and slow writes, or if they would rather have 1 file per process total. You still have the same problem you have, but I guess a fourth of it.
We have another one. Why don't you just go with stats exporter?
So this is where I fess up that I'm not the stereotypical SRE. And so to be honest, I don't know. So in my company, we didn't want to go with that one. I don't remember the exact discussion around it. I don't remember the exact reason, but like it wasn't ideal for our use case. But I don't really have a good answer. I'm sorry.
Okay. Then the other obvious question: when will you rewrite everything in Rust? Because that's the.
So.
Oh no!
So here's, well, there's another trade-off there, right? So with the system now where you have the interchangeable stores, you could have a store written in Rust. And then if you can do the magic memory thing there, then you don't need to be dealing with the files. And then the exporter is still written in Ruby, which kind of sucks. But if you put that store in a separate gem, then it's great. The reason we don't want Rust or C code in the main exporter code is that then you exclude the JRuby people, which I think it's not a majority of us, right? I think it's nice to support them, particularly because they don't have this problem. They can actually just have a hash in memory because they're not doing multi-process in general. So ideally, no. But I haven't discarded it as an option. It can totally be a separate gem, and I'm trying to figure out how we can have like a Rust exporter and a Rust store, and they can talk directly to each other. And then it sort of breaks my beautiful abstractions, but it could be the way to make this fast for MRI people. So C Ruby people.
For the record, I was joking, but
no, I know you were, but we're actually considering this because we want to make this better, and also Rust is fun, and a bunch of people want to play with it, and this is a great excuse. So yeah.
So we're basically out of time, but we have one good question, but we need to be quick about that, and then we will pivot over to lightning talks. Did you ever exhaust all available inodes because of the file parametric process approach? Is this a major concern?
Yes. So we haven't. Other users of the gem have. It is a major concern. It's the too many files problem, and is part of what I want to fix.
Mm.
All right. That's it from me.
Thank you.
Thank you very much.
And retweet your setup so more people can see.
Yes, I'll tag you guys in there.